Hey guys, in this video we're going to be going over the first recitation packet for Dr. Collini's Chem 2380 class. And as you can see, the title was wrong, so just ignore that. I'm going to fix it here. Question 1 asks us to define a reduction reaction, so I'm going to write down the two mnemonics that are most commonly used for redox chemistry, and that's either oil rig or Leo says GR. So either oxidation is losing, reduction is gaining, or loss of electrons is oxidation, gain of electrons is reduction. Both of those are saying the exact same thing, just with two different mnemonics. So again, reduction is gain of electrons or electron density. So what I mean by this is the thing that is reduced is going to become bonded to something less electronegative than before, because when it's bonded to something less electronegative, it's therefore going to have more electron density around it. So it gained electron density, which means that it was reduced. In most of the examples that we see in this packet, the thing that is reduced is going to become bonded to hydrogen atoms, because hydrogen atoms are less electronegative than the oxygen atoms that they were previously bonded to. So if you go from being bonded to oxygen to being bonded to hydrogen, you are reduced because you are now bonded to something less electronegative. Question 2 asks us to draw the progression of a reduction reaction beginning with carboxylic acid. So if you start with carboxylic acid and you reduce once, you will end up with an aldehyde. If you reduce a second time, you will end up with a primary alcohol. Notice that the carbonyl carbon goes from having 3 bonds to oxygen to only having 2 bonds to oxygen, to finally only having 1 bond to oxygen, and in each case, the previous bond to oxygen is replaced by a bond to a hydrogen. Next, we're going to do the same thing, but we're going to start with a ketone. So we have 2 bonds to carbon and 2 bonds to oxygen, so we can only reduce this once, going to a secondary alcohol, replacing one of the bonds to oxygen with a bond to a hydrogen. In question 4, we are asked to draw a mechanism for the reduction reaction between a ketone and a hydride ion. And just as a reminder, the hydride ion is typically going to come from either sodium borohydride, which is NaBH4, or lithium aluminum hydride, which is LiAlH4. Both of those are capable of reducing a ketone. Before I draw any arrows, I think it's important to identify the nucleophile and electrophile in the reaction. So the nucleophile is the thing that is electron rich. It wants to use its electrons to form a bond. And then the electrophile is the thing that has the least electron density. So in this case, it will be the carbonyl carbon because it's double bonded to the oxygen, which is going to be pulling electron density away from it. So the carbonyl carbon is the most electrophilic position. So I'm going to show the hydride ion attacking the carbonyl carbon, which is then going to push up one of the bonds from the carbon onto the oxygen. So we're left with a negatively charged oxygen and a newly formed bond to hydrogen. Step 2 is just an acid-base reaction. So now that we've formed an alkoxide ion, we just need to add some sort of acid to the solution so that the alkoxide can react with the acid and produce an alcohol. And I've drawn the first proton in red because that was the hydride that did the attacking, and then the second proton is in blue because that was an acidic proton, or an H+, that was attacked by the oxygen. So again, step 1 was the nucleophile attacking the carbonyl carbon, which is shown here, and then the second step is where the oxygen is protonated, again as shown here. Question 5 asks how the reaction above would proceed differently if we used an ester instead of a ketone. So I'm going to draw that ester, and starting with the same reactant, we have an H-. The first step is exactly the same. We're still going to attack at the carbonyl carbon and kick up the double bond onto the oxygen. However, instead of immediately protonating the O-, those electrons are actually able to come back down and reform the carbonyl carbon by kicking off the OR- as a leaving group. In doing this, we create an aldehyde where the hydrogen in red is the original hydride ion that attacked at the carbonyl. And since we have reformed the carbonyl carbon, we can actually have a second hydride come in and attack the same way as before, creating an alkoxide ion, which now this is just exactly like before. There's nowhere else for those electrons to go. So I'm going to scoot this over so we have a little bit more space. And again, I just want to highlight the hydrogens so you can see where they're all coming from, because in step 3, we're adding in an acid. So this is an H+ ion, which is attacked by the alkoxide ion, which creates the alcohol. And I'm going to draw this one in green so you can see that it's different from the previous two. Question 6 asks about the hybridization of the carbonyl carbon before and after the reduction. So before, the carbonyl carbon has 3 electron domains. When it's formed into an aldehyde, it still has those 3 domains, but when it becomes an alcohol, we now have 4 electron domains around that carbon. So the reactant, or the ester that we started with, had 1 s orbital and 2 p orbitals, which is an sp2, and the product had 1 s and 3 p orbitals, which is sp3. Moving on to question 7, I'm going to start by drawing out all of the functional groups because I think it's helpful to visualize them. So we have aldehyde, ketone, ester, and carboxylic acid. The first two are capable of being reduced by sodium borohydride, which is a weaker reducing agent. If you want to be able to reduce the ester and the carboxylic acid, you need to use lithium aluminum hydride because it is a much stronger reducing agent. So that's the end of the reduction portion of this packet. Moving on to oxidation. Remember, oxidation is loss of electrons or electron density, so in my own words, the way that I think about it is the atom that is oxidized becomes more electrophilic because it becomes bonded to something that is more electronegative than before. So for example, if you started out by a carbon being bonded to hydrogen, and then the hydrogen is replaced with oxygen, the carbon in that bond is now more electrophilic because the oxygen is pulling more of those electrons away from the carbon. If we were to draw the progression of an oxidation reaction beginning with a primary alcohol, it would first convert into an aldehyde and then into a carboxylic acid. So notice on the alcohol, it starts by having 2 bonds to hydrogen and 1 bond to oxygen. The aldehyde then has 1 bond to hydrogen, 2 bonds to oxygen, and finally the carboxylic acid has 3 bonds to oxygen and no bonds to hydrogen. If we instead started with a secondary alcohol, this oxidation reaction would only be able to happen once because there's only 1 hydrogen that can be removed, so we can only add 1 extra oxygen onto this compound. And again, we can tell that it's been oxidized because the carbonyl carbon started by having 1 bond to oxygen and ended with 2 bonds to oxygen. A tertiary alcohol cannot be further oxidized because there are no hydrogens that can be abstracted, so this will have no reaction. We talked about 3 reagents in class that are capable of being used for oxidation reactions, and those were PCC, the Jones reagent, and potassium permanganate. So let's talk about each of those. PCC, otherwise known as pyridinium chlorochromate, is capable of oxidizing primary alcohols into aldehydes and secondary alcohols into ketones. And I'm going to shrink this down just a little bit so that we have room for the other 2 reagents. So next is the Jones reagent. This is also known as chromic acid, and it is made by taking chromium trioxide and sulfuric acid and reacting them together to create H2CrO3, which is chromic acid. Chromic acid is a stronger oxidizing agent than PCC, so if it reacts with a primary alcohol, it will create a carboxylic acid. However, if it reacts with a secondary alcohol, it still just creates a ketone. And again, I'm going to shrink this down just to save space, so don't mind me here. And the final reagent is potassium permanganate, or KMnO4. This basically does the same thing as the Jones reagent, so it's able to take primary alcohols to carboxylic acids and secondary alcohols to ketones. However, you'll remember from Organic Chemistry 1 that potassium permanganate can also react with double bonds, like carbon-carbon double bonds, and depending on whether you use hot or cold KMnO4, you might get 2 different products. I'm going to draw a quick example for you to remind you what I'm talking about here. So I have trans-2-butene, and depending on whether it's hot or cold, I'm going to get 2 different products. So, actually let me change this to red just to make the colors make sense. If it is cold, we will get a diol, where 2 alcohols are added in a syn addition on either side of the double bond. And if it's hot, we are going to cleave that double bond right down the middle and put an oxygen on either side of the double bond. For the remaining problems in this worksheet, we're going to identify if the reactions are oxidations or reductions, and then identify the major product. So in the first reaction, we have sodium borohydride, which you can just visualize as an H-, and it is reacting with a ketone. So because we have H- and a ketone, this is a reduction. This means the H- will act as a nucleophile and attack at the carbonyl carbon, creating a secondary alkoxide, which can then be protonated by the H2O in solution, creating an alcohol. Up next, we have PCC and a primary alcohol. So this is going to be indicative of an oxidation. And because it's PCC, it's going to convert the primary alcohol into an aldehyde. Up next, we have O3 and DMS reacting with an alkene. And as you'll notice, this is not one of the reagents that were discussed earlier in this assignment. This is a review reaction from first semester organic chemistry. So take a second and pause the video if you want and try to remember what the products are for this reaction. Okay, if you said oxidative cleavage, you would be correct. When these 2 reagents come together, the double bond is broken in half and either ketones or aldehydes are formed in their place. And because we are adding bonds to oxygen, this is an oxidation reaction. So now every time I draw cleavage reactions, I always draw them with just a really elongated single bond on one side. That way I have space to add in the two oxygens on either side of the double bond. I know it looks kind of funky, but then I just rotate it and then it looks normal and it makes sense. Just make sure when you rotate that you count all of your carbons to begin with and make sure that you don't lose any carbons along the way. So in this case, there were 8 carbons, so I'm going to draw 8 carbons, and the carbonyl carbons are on carbon 2 and 7. Up next, we have a reaction between lithium aluminum hydride and an aldehyde. So this is going to be a reduction reaction. And in reduction reactions, we have basically an H- that's able to act as a nucleophile and attack at the carbonyl carbon, which will then create an alkoxide ion that in step 2 is then protonated to create a primary alcohol. The next reaction is another O3 and DMS reacting with an alkene. However, there's also an alcohol on this reactant, so this reaction is here to point out that while O3 and DMS is capable of oxidizing double bonds, it is not capable of oxidizing alcohols. So the double bond will react and the alcohol will remain unreacted. This is still considered an oxidation reaction though, because we are still adding oxygen onto the double bond. So again, I'm going to do the same thing as before, where I just insert 2 little oxygens where the double bond used to be, and then leave the alcohol where it was. To make the molecule look a little bit more normal, I can again rotate, and I'm going to do this by counting all of the carbons in my chain, and in this case there are 5 carbons, so I'm going to draw a 5-carbon straight chain, and there are carbonyl groups on carbons 1 and 5, so I'm going to add those in, and then the alcohol group is on carbon 2. The next reaction is almost the exact same, but instead of O3 and DMS, we have KMNO4, which is again an oxidation reaction. And it's going to cleave the double bond just like before, except instead of aldehydes, the KMNO4 is a stronger oxidizing agent, so it creates carboxylic acids, and it is strong enough to oxidize the alcohol into a ketone. We can again rotate this molecule to make it look a little bit more normal to our eyes, so I will do the same process as before. I'm going to count the 5 carbons in the chain, and then draw them all in a straight line, adding the carboxylic acid groups to either end and the ketone on carbon 2. As I was editing this video, I just now noticed that I forgot to specify whether KMNO4 was hot or cold, so for that first reaction, we can assume that it was hot because there was a cleavage. If instead we had done KMNO4 in a cold solution, we would add the diol across the double bond. If we were to take the same reagent and use PCC as the oxidizer, we would be able to oxidize the alcohol into a ketone, but the alkene would remain unreacted because PCC does not react with alkenes. The next reaction is lithium aluminum hydride reacting with an ester, so the H- is going to attack and the electrons on the oxygen are going to come up and then down and then kick off the leaving group. So this is a reduction because we are reducing the oxygen content. And again, the first step is the hydride attacks, and the oxygen is then going to kick off the leaving group, which will leave us with an aldehyde, which is then subject to another attack from a hydride ion, which creates an alkoxide ion, which can then be protonated by our second step, creating our primary alcohol. And if we draw in all of our implied hydrogens, you can see that the starting material started with no hydrogens, and then the intermediate had 1 hydrogen, and the final had 2 hydrogens, so this is in fact a reduction. If we were to replace the lithium aluminum hydride with sodium borohydride, there would be no reaction because sodium borohydride is not a strong enough reducing agent to react with esters or carboxylic acids. And that brings us to the end of this recitation packet. As always, if you have any questions, feel free to send me an email or come talk to me after class.